Okay, welcome everyone to the OpenACC course. Thanks a lot for joining us today. It is 9 a.m. here in California, and we're ready to go full speed with OpenACC. My name is Julia Levitas. I'm a product manager at our Tesla group, and we'll help to kick off this first class today. So let me start with some logistics. First of all, every session of the course will be recorded and available for you to review on our OpenACC course. So I believe everyone already checked this page, and we'll have a link for you later as well. So all the lines are muted right now, just to make sure that the audio is crisp for everyone. So please submit your question through a Q&A pod on the left side of the screen. It's at the very bottom. We'll also do our best to answer all the questions today, but we might not get to every single one of them. So for that, we will have another session on Tuesday, October 6th, where we'll get to the rest of the questions. And also, I believe it's probably enough of me talking, so let's get to work. I would like to introduce you our instructor of the class today and assure that you are in really great hands. So Jeff Larkin is a software engineer in NVIDIA Developer Technology Group, where he works on porting and optimizing HPC application. He is also closely involved with the development of both OpenACC and OpenMP specifications. So Jeff, we're ready to start.
Thanks, Julia. Welcome, everybody, to this course on OpenACC. I do want to start things off by giving you a brief introduction of what we can expect from this course and show you what we'll be teaching about. And first, I want to present to you the course objective. And our objective is to enable you to accelerate your applications with OpenACC. Throughout the course, we'll be giving you some code samples, some times on hands-on labs. All of these will be made available to you for free, but our goal is that through learning on those codes, you'll be able to take the applications you care about and make them run well on GPUs and on other platforms with OpenACC. This is the course syllabus. Of course, we're in week 1 here, and as Julia mentioned, that we're going to be alternating weeks. 1 week will be a lecture, so this is week 1. Next week, we'll have office hours on Tuesday, and the week after that, we'll have the next lecture. Today's lecture is meant to be a complete overview of what you'll see throughout the course, so you'll get some high-level tidbits from everything, and then in future weeks we'll go into a lot greater detail about each of the topics, with the next lecture being specifically about how to profile your application and how to parallelize it with OpenACC. So I hope you'll come back for each of these topics, and today we'll just give you a little taste of what to expect. So here's the agenda for today. First, I'm going to give you an idea of why you should be using OpenACC, why we care about it, and why we support it. Give you some really basic fundamentals of accelerated computing, introduce you to the programming cycle that we're going to use throughout this course, and then at the very end I'll discuss a little bit about the OpenACC toolkit, which is a product from NVIDIA that you can install freely, the quick lab system where you'll be doing your homework, and assign to you the week 1 homework. So, why OpenACC? I think many of you are here because you're interested in GPU computing, and for OpenACC, this is a way that we can bring GPU computing to a lot wider audience. So OpenACC is designed to be simple to use. So we can see here in the top left bar there a pretty simple code sample here, and the thing to notice is all I've had to do to use OpenACC is add compiler hints. In C and C++, these are known as pragmas. In Fortran, these are known as directives. I add those to the code and allow the compiler to do a lot of the heavy lifting for me, to figure out how to move my computation, move my data to the GPU, and bring it back. So it's really simple to use. You can add it to your existing codes. However, it's still very powerful. You can still get very good performance using OpenACC. We've highlighted 2 samples here. One is from the University of Illinois, doing a medical imaging program, and you can see here that in roughly 2 days of effort, they were able to get a 70x speed up using GPUs. Now, seeing a number like that, that probably means they're starting from a single core serial application and bringing it to the GPU, and so that's why you see such a large speed up. Another highlight here is from Riken in Japan. They took a climate model called NICAM, and you can see here they achieved somewhere between a 7 and 8x speed up, only modifying about 5% of their source code. So as opposed to a more explicit programming model like CUDA or OpenCL, very small code changes, you can see a very nice speed up. And in this case, this is probably a more fair socket-to-socket comparison, a full socket or many full sockets of CPU versus the GPU. The last thing to highlight about OpenACC is it's designed to be portable. It's designed in such a way that all of the decisions that we as the OpenACC standards body make, we have to look and say, is that unique to NVIDIA GPUs or AMD GPUs or CPUs? If so, it doesn't belong in the specification. We really want something that is going to be fully portable to all devices. And so we believe OpenACC will really fuel the next wave of scientific discoveries in high-performance computing. And part of the way that it's going to do that is make GPU computing and accelerated computing much more approachable to domain scientists. And so one code we really like to highlight here is the LS Dalton code. This is a chemistry code, and specifically the linear scaling LS Dalton is being developed at Aarhus University in Denmark. The developer we're highlighting here, Janus Juel Eriksson, he is a PhD student in chemistry. His background is in chemistry, and he understands enough Fortran to be able to do computational chemistry, but he's certainly not a computer scientist. And so for him, something like CUDA or something like OpenCL just really was too much effort for him as a non-computer scientist. So he came in with his Fortran code and used OpenACC, and you can see here he had very nice results, where he modified less than 100 lines of source code in his application, took him less than a week of effort, and he was able to get here on the Titan supercomputer in Oak Ridge anywhere from 8 to 12x on real science problems. And so this was a real big boon to him, and it made OpenACC enabled him to use GPUs to get his science done. And one more thing that's important to highlight here is he has one source code. So there's not a unique GPU port of his code and a CPU port of his code. He has one source code that will run everywhere. And so we believe OpenACC is a really powerful technology that allows that. If you've not seen OpenACC before, or maybe you've not even seen directive-based programming before, here's what things look like. So you can see I have a really simple for loop here that does a vector sum. And there's three types of directives that you can use. Now in C and C++, directives take the form of compiler pragmas. So compiler pragmas are additional information and instructions you can give the compiler, and if the compiler doesn't understand what they mean, they can simply ignore them. So you can see we have directives for initializing parallel execution. So the parallel directive here offloads to the GPU and makes things run in parallel. There are directives for managing your data. So rather than having to have a unique GPU copy of every array and a unique CPU copy of every array, all of that is managed for you by these directives. And then there's some optimization pragmas as well, where you can really, if you know you're going to be running on a very particular piece of hardware, you can really tune your code to run well on that. All of this can be added incrementally to your source code, and that's how we'll be coding during this course. It allows you to maintain a single source code for all architectures, CPU, GPU, Xeon Phi, whatever architecture you choose. And it's important to know it's also fully interoperable with other programming models. And so you can use OpenACC along with other technologies such as CUDA and accelerated libraries. And lastly, it's designed to be performance portable. And what I mean by that is because we're expressing our parallelism at a high level, you can take this same code and make it run on a variety of platforms. And it should run well everywhere. Now obviously the more you tune your code, the less portable it will be, but it's really designed at a basic level to be performance portable. Okay, so that's why you should choose OpenACC. So let's talk a little bit about accelerated computing and what I mean by accelerated computing. For most of us in our laptops, certainly in many of the top supercomputers, even in our phones, you'll find that we have two different types of processors in those devices. We have a CPU, and CPUs are the traditional type of architecture that's designed to run serial tasks really well. So you have a small number of cores, you have these large caches of memory, and these cores run at a very high clock speed. So if you have a small number of tasks, they're going to run really fast on the CPU. But most of the time these days, you also have a GPU on board. And GPUs are designed for parallelism. They're designed to get high throughput on very data parallel problems. So if you think about the root of where GPUs came from, graphics processing, you think about an image has lots and lots of pixels. Each of those pixels can be worked with independently. And so GPUs work with very independent pieces of data in parallel to achieve high throughput speed up. And in accelerated computing, the important thing is to use both. And we believe there are going to be some parts of your program that will run really well on a CPU, and some parts of your program, the beefier parts, the parts where you're doing the bulk of your science and the bulk of your calculations, those can be done in parallel on the GPU. So how would you program for a machine like this, where we have these two heterogeneous architectures? So a homogeneous architecture would be running on one or the other, and heterogeneous is where we're running on two different architectures at the same time. So if we take this box down the middle as represents the time of your program execution, we'll start off running on the CPU and work through the sequential parts of our code. But at some point, we're going to hit a function that is really important, has a lot of work to be done. It takes up a large percentage of your time and a small percentage of your code. And for that, we're going to offload that part of the computation to the GPU. The GPU is going to work on the highly data parallel, the highly compute-intensive parts, and then when it's done, you move back to the CPU for the rest of the sequential parts of your code. Now, ideally, the bulk of your calculations, you'll have these large, beefy functions where you can offload a few key functions to the GPU and see a real substantial speed up in your code. And the key is, of course, that we want to leverage the strengths of both of these architectures. So how do you program for a machine where we have to deal with these two distinct architectures? We believe there's three approaches that you could take. They live along this spectrum of portability and performance, where things that are more portable have a tendency of being less performant, and things that are more performant tend to be less portable. Accelerated libraries are a very portable way to write your code. And most of the time, they're also very high performance. You can, without making any changes to your code in many cases, get high performance speed up. However, you're really limited by what libraries are available. So if you're doing a lot of matrix algebra, if you're doing a lot of fast Fourier transforms, common operations like this, you may be able to accelerate your application right away without making any changes to your code. As soon as you fall out of those common libraries, however, you need another approach. For that approach, we have compiler directives. Compiler directives are designed to be very portable, and they're at a very high level. So they're based on existing programming languages. In the case of OpenACC, you can use C, you can use C++, you can use Fortran. And all of it is familiar to use because you're staying in the language that you already know and adding additional information to your code. The trade-off is that because it's at a higher level, the performance is not always optimal. And what I mean by not optimal, many people say, well, how fast can OpenACC be in comparison to CUDA? And that's a difficult question to answer because it requires having a code that's written in both. But in the cases where we do have codes written in both, what we're finding is OpenACC most of the time can get somewhere in the ballpark of 90% of CUDA. In some cases, completely on par with CUDA. In some cases, a little less. But on average, we're seeing most codes can be around 90% of hand-tuned CUDA. So that's still very good performance. But if you need the absolute best possible performance, we have parallel language extensions like CUDA and OpenCL. These give you complete control, a lot of flexibility to get the maximum possible performance out of your code. But of course, they tend to be less portable because you're writing at such a low level detail about and optimizing your code in that way. They also tend to be more time consuming to implement. Now, the good news is you don't need to choose one of these approaches up front. And in fact, for most of us, there is no one perfect approach. In fact, they all work together. So the approach that I like to advocate is starting your code running with accelerated libraries as much as possible. And the OpenACC toolkit that I'll discuss towards the end here provides you with a variety of accelerated libraries that we at NVIDIA have already tuned for you. So the great thing is if you use these libraries, when the next architecture comes out, your work is done. We've already hand-tuned these libraries for you. When you run out of what you can accelerate with libraries, the next step up is to use directives. Directives allow you to very rapidly accelerate your code adding these incremental changes and getting more and more running on the GPU. And what's great here as well is it's portable. So using these directives, any change I make can be applied on other architectures as well. And then when I reach a point where I have a function that I need the absolute best possible performance, then I can use something like CUDA to get the best possible performance in a very limited level. And by using all of these together, I get a code that is fully portable to any architecture and also performs very well. Now, for the bulk of this course, we're going to be focusing on this middle bubble, which is the OpenACC directives. However, later in the course, you'll see examples, and you'll actually do some examples where we're using OpenACC along with accelerated libraries and along with CUDA, so you can see how that's done. Okay, so let's look at how we program with OpenACC. I advocate this cycle when I'm teaching and when I'm accelerating applications with OpenACC. The first step is to profile your code and identify where there is parallelism in your code. Find these important functions. Find these important, really beefy loops, and look at those and find the parallelism. Next is to express the parallelism in the code. And the reason I say express parallelism is I'm providing information to the compiler about where there is parallelism. I'm not actually doing the parallelizing myself. If I were writing in CUDA, I would be breaking down my work into the small parts. I would be explicitly managing how that's run on the GPU. With OpenACC, I'm simply expressing where there's parallelism, and I'm allowing those lower level details to be decided by the compiler. And then later on, we can discuss how to optimize that. But for now, let's just get things parallel. Now usually what happens, because the CPU and the GPU have two distinct memories, is I put a lot of parallelism in my code and my code slows down. It's a really common thing to happen. So the next step is to take my knowledge about how the data is used and where I need it on the CPU, on the GPU, and express that to the compiler. And at this point is when we usually see significant speedups. And so we really have to follow through to that part. And then lastly, if I still find there's more performance to be had, I can further optimize my loops. And usually, for most codes, this is the last 10% of performance. It's really not a lot of performance to be gained here. The bulk of your speedup, when we see things like 7 and 8x speedup numbers from these real applications, most of that has come in the first 3 steps, and then we get the last few percent in that last step. Now, I'm going to give you a simple example here where I walk through these steps. Come back in 2 weeks, and we're going to focus on a lot of detail on these first 2 steps, and then in lecture 3, we're going to focus a lot more on the second 2 steps. So the code I'm going to be using is a Jacobi iteration. This is the same code that you'll be doing in the homework this week. So take close notes, and I'm going to provide you most of the answers for this week's homework. This example is a stencil operation where I'm iteratively converging on some value based on the values of my neighbors. So if we look at point x, the point in the middle here, this gray point, for each iteration through the loop, I'm going to calculate my value for that gray dot based on the average of its neighbors, the 4 yellow dots. That's what this formula says here. These types of approaches are really common in a lot of scientific applications, and it turns out they fit really well on a slide. So we tend to teach with this code first, and then I have another code that will show you a different type of application in 2 weeks. So here's what the code looks like. This outer loop is our convergence loop. And you can see here I'm going to keep iterating over and over again until one of 2 things occurs. Either I reach some maximum number of iterations, which in all of the examples, all of the performance results I show you will be 1,000 iterations, or I've determined that my answer is close enough and it has reached this tolerance level. That's when I call it converged. This next nest of for loops, I go across all matrix elements. I figure out my next value based on the value of my neighbors. And then lastly, I figure out what's known as the error value, and that error value is the rate of change. When my value stops changing very much, that's when I call it converged. And lastly, I have a second set of for loops here where I swap the input and output arrays. Now, one thing I'm constantly asked when I show this code is, couldn't I have done something like a pointer swap that would be more performant? And yes, there are Better ways to do this in real scientific applications, but by illustrating this way, I think it's a lot easier for us to talk about and easier for people to understand. So the first step is to identify parallelism. Now, normally I would go through a lot of information about how to find the hotspot in your code and identify the important loops. I'm going to jump ahead a little bit to the point where I've identified that this loop nest I've already shown you is the important kernel within my code. Now, if I look at this outermost loop, is this loop something that can be parallelized? And the answer is no, and there's really two reasons. First, there are data dependencies between each iteration. So every iteration I requires that iteration I minus 1 has completed. And in the case of course, the first iteration, we have the input values for that. But we'll constantly have this data dependency moving forward. So that means we're not going to be able to parallelize. The other thing to note here is that this loop is not countable. And what I mean by that is the compiler cannot, at compile time, determine how many iterations this loop will make. It can see that perhaps it would get at most max iterations, but we can't see for sure how many iterations this will take. We actually can't even tell for sure that this will ever complete. And so because of that, we also cannot parallelize this loop. However, for the two for loop nests, those have fully independent iterations. So for every iteration through I and j of this top loop, you can see I'm storing into one space in A new, and I'm reading from A. And so no iteration affects the other iterations. And the same is true down the bottom. So these loops are safe to parallelize. So now that I have identified where there's parallelism in my code, I need to express that to the compiler. And to do that, I'm going to use an OpenACC directive. In this case, I'm going to use the kernels directive. Now, the kernels directive identifies a region of the code where I want the compiler to analyze and find parallelism for me. So up at the top, I say this identifies a region that has loops that I believe the compiler can turn into kernels. And I'll go into more detail about kernels in the future lecture. But basically what I'm saying is a kernel is something that can run in parallel on a GPU, and I want the compiler to look in here and find where it can generate parallel work on the GPU. So here I have two sets of loops, and each of those will be generated into a parallel kernel. So let's apply that to our example code here. You can see my outer convergence loop I've already determined is not parallel. And so I'm not going to put a kernels pragma around that. However, these inner loops I know are. So I'm going to add an ACC kernels here, and it's actually going to end here. My coloring is wrong on this slide, but it ends here. So I've wrapped my for loops with this ACC kernels, and I'm asking the compiler, find the parallelism here and parallelize it for me. Now, throughout this course, we're going to be using the PGI compiler because this is something that is freely available to you through the OpenACC toolkit. And it's going to be available to you on our labs as well. So to build with the PGI compiler, I have my PGCC here. If you're a C++ programmer, it would be PGC++. And if you're a Fortran programmer, it would be PG Fortran. -fast is my optimization flag. So that's something like 02, 03. -fast is the preferred flag. This TA equals Tesla turns on OpenACC. So TA stands for Target Accelerator, and Tesla is for the NVIDIA Tesla GPU. The last important thing here is the minfo equals all. And what that does is it tells the compiler, hey, tell me what you're doing, so I can look at it, make sure I understand what you're doing. And that's really important when optimizing your code, to understand what the compiler is doing. In this case, you see at line 57 and 59, that's our top loop nest. It found those loops to be parallelizable, and it generated an accelerator kernel. Same thing with the lower loops, 67 and 69. It generated an accelerator kernel for those as well. So now that we know we've generated accelerator kernels, I would expect, of course, things to run fast. They're going to run on the GPU. This is a parallel operation. It's going to run really fast. So let me show you the performance. Here is our single thread baseline. You can see as I add CPU threads, things speed up. And then I add the GPU and things slow back down. Why is that? And I should note here this is using PGI 15.7, and this is a modern CPU and an NVIDIA Tesla K40 for comparison. So what happened here? And I kind of already spilled the beans a little bit, but it turns out that by default, I'm going to get way too much data movement between the CPU and the So one of the ways I can tell that is using a tool like the NVIDIA Visual Profiler. So again, I'll show you more about how to use this in a future week, but jumping straight to the punchline, if I run through the Visual Profiler, it's going to tell me that I have a low compute to memory copy ratio. And so what that means is for the amount of time spent actually doing work on the GPU, which is about 5 seconds, I have way more time spent copying memory, in this case about a minute. So we need to fix this. We need to find out why I'm spending so little time computing and so much time copying memory. If I zoom into just 2 iterations, we can really see the answer here. So this is one iteration on the left and a second iteration on the right, and we can see the teal and the purple are where I'm computing on the GPU, and these tan colors are where I'm copying data. The top bar is copying from the CPU to the GPU, and the lower bar is copying from the GPU back to the CPU. All right, so let's figure out why this is happening. So again, here's my outer while convergence loop, and as soon as I come in, my 2 arrays are on the CPU. It's going to encounter the ACC region, and it's going to copy from the CPU to the GPU. It's going to compute there, and then when all is said and done, it's going to copy the data back and go back around for the while loop. So why is it doing this? Why is it copying so many times back and forth every single iteration of loop? Well, if you think about what the compiler knows versus what we know, it's really not making a bad decision. It's trying to be safe and make sure it's giving you correct answers. So if I go over to look at this in more detail, here's my code. And between the 2 for loops, between the 2 nests, does the CPU need the data? Well, it turns out no, because there's no code in between here. So we know we can leave our data on the device through that section there. And the compiler knows that because I have this kernels region, so it knows everything possible about this region enclosed with the kernels. But as soon as that kernels region ends here down at the bottom, it can't determine whether or not I'm ever going to need the results back. And so it has to assume I will. So I reach that. It says, hey, you've modified A new. I better copy them back to the CPU just in case you need them in the future. Well, most of the time what happens is as soon as that ends, I go right back around for another iteration, and I'm going to copy them back. So I can see as the programmer that when I really need the data is I need to copy it in at the while and copy it out when the while completes. But the compiler can't see the big picture, so it has to be more cautious. So it's doing a lot more data movement than we would hope. So the next step is to express ARM knowledge about data movement to the compiler. And we're going to use the OpenACC data region to do this. The data directive identifies a block of code, a region of code, where I want my GPU arrays to stay on the GPU. And so you can see here, if I have 2 ACC kernels regions wrapped with an ACC data region, that these kernels regions will share those arrays. Now, I can actually do something better, and that is to tell the compiler explicitly how I want the data to be moved. I'll do that with data clauses. So here are the valid data clauses. The copy clause says, at the beginning of this data region, take a copy of my array and copy it from the host to the device, so from the CPU to the GPU. And at the end of the region, I need the results back. So copy it again back from the GPU to the CPU. Copy in and copy out are one directional. Copy in copies into the GPU, copy out copies back out from the GPU. And then a create only generates space on the GPU. It creates space, but you're telling the compiler, I don't care about the initial values and I don't care about the ending values. Lastly are present and device pointer, and they'll be discussed at a later time. One more thing you need to know about these data clauses is that frequently you need to tell the compiler about the shape and size of your array. So this is particularly true in C and C++ because arrays in C and C++ are just pointers. And so the compiler doesn't know how much space is being pointed to. In Fortran, the arrays include shape information, so the compiler can already handle a lot of this for you. So here I see ACC data copy in of A, and I'm going to tell the compiler this array starts at element 0, as C arrays do, and I want to copy n elements to the GPU. So now I've told the compiler the size and shape of my array. And of course, I can also provide parts of the array, and that's what the second part here is. If I have only want a certain part of B, I can specify that. You can do the same thing in Fortran. If you're copying the entire array, you really don't need to specify the starting and ending values. But if you're doing partial arrays, you do. There's a subtle difference between C and Fortran. In C, you say the starting element and the number of elements. In Fortran, you say the starting element and the ending element, and that's just because the languages work a little differently. Last thing to note is the data clauses can appear on data regions, on parallel regions, and on kernels regions. So I've only discussed 2 of those so far. So let's take our code and apply our data knowledge. So you can see I've added a data region around my while loop. So because I haven't put any curly braces here, it actually applies to all of the while. I'm going to tell the compiler, when you encounter this region, I need to copy the input values of A in, and I need to copy the output values of A back out at the end of this while loop. However, A new, it turns out, is a temporary. So I don't actually need to copy the data back and forth. So I'm going to use a create clause. Handle that. So adding these to the arrays, what I would expect is A new is a temporary that would only be used within the while loop, and A would be copied before the while loop begins and again as the while loop ends. So I'll rebuild the code, and you can see that the compiler has generated code to respect that here at line 51, copy A to and from, and copy A new back out. And if I go back into Visual Profiler, you can see things look a lot better. So if I highlight 2 iterations again, what I have here is each iteration happens back to back. There's still a tiny bit of data motion, and what's happening with those tiny little slivers here is that's the value for error. So I'm calculating the error value on the GPU, and I need to copy it back so I know whether I've converged and whether I can stop. All right, so let's talk about the performance. So whereas before I was running at about 90% of the original, you can see now things look a lot better. So I can scale up to 8 threads. And by the way, the CPU does have 16 cores. The performance beyond 8 cores flattens out, so I've only shown 8 here. And you can see socket to socket, I'm running about 5x faster than a full CPU socket here. So things look a lot better now that I've informed the compiler how to handle the data motion. So now we're running on the GPU. The last step in the process, as I said, is to optimize your loops. And I'll show you a little bit of an optimization on this code. And again, we're only going to get a small percentage. The loop directive is a way to tell the compiler some additional information specific to the next loop. So what you would do in the case of a for loop is the next line above that, add a loop directive. And some of the clauses that you can give. One is an independent clause, and that tells the compiler all of the loop iterations here are independent with respect to each other. And so even if the compiler can't figure that out for itself for some reason, and one reason that frequently happens in C and C++ is pointer aliasing, the loop directive, you can tell the compiler, hey, I promise you these loop iterations are independent, and therefore the compiler doesn't have to analyze it. It can just simply parallelize it for you. The collapse directive is one where if I have 2 loops that are tightly nested, so no code in between them, that I can collapse them together into one flattened loop. This is really useful if I have a whole bunch of loops, 5 and 6 loops deep, but they don't have a lot of iterations by themselves. If I collapse some of them together, I'll have more parallelism to use. So I might, one case I've seen before, I have a 4x4 loop nest, and so I will collapse the two of them together to make it a loop of 16, which has more parallelism. And then the directive that I'll be using here is the tile directive. And the tile directive takes a loop or set of loops and breaks them up into chunks of work. And so when you have an application like these stencils where a lot of the work happens in very localized areas, one optimization would be to work on tiles of work. You can do that manually, or here you can tell the compiler to do it for you. So I'll show you that in our code, it turns out that if I tell the compiler to tile the j and I loops, in this case it's going to tile by 32. So I'll take 32 iterations of the j loop and 4 iterations of the I loop and generate tiles with them and operate on those. And that turns out to be the best way to run this on an NVIDIA GPU. Now there's actually a typo on this slide. I'll fix them on the final slides we post. This device type clause should actually be in front of the tile. And the reason I have that is I have only tested this optimization on NVIDIA GPUs. And so I don't want the compiler to apply this optimization everywhere. I only want to apply it on NVIDIA GPUs where I know it helps. So the final slides that we'll post online will have that corrected. That should go in front. So you can see by adding this to the loops, I get about 10% higher performance. So again, we got most of our performance in the first 3 steps and a little bit more by tuning it. So that's the end of this particular case study. I really hope you'll come back in 2 weeks. We're going to start a completely different application and go with a lot more detail at each step, exactly how to profile, exactly how to parallelize, and so on. So I really hope you'll come back and see this, see the next code example. I do want to close out this course talking a little bit about the OpenACC toolkit. This is a product that we very recently, back in June, made available. And so I hope that some of you have had a chance to look at it. I see a comment that the audio and the presentation is getting out of sync, and I apologize. I think there's a Wi-Fi issue on my end, so hopefully we can get that realigned for you in the final video. The OpenACC toolkit is a free toolkit we've provided on our website, developer.nvidia.com/openacc. It includes a whole bunch of tools for you. First is the PGI compiler. So the PGI is one of several OpenACC compilers that we're making available to you. Now, if you happen to be associated with an educational institution, if you're a student or a professor, for instance, you can get a completely free compiler. This license is good for 1 year, and it's renewable for as long as you're at that university. If you are not an academic, you can still download this, and you will get a 90-day trial license, which really should give you more than enough time to evaluate OpenACC and decide whether this is worth a purchase for you. We've also included several tools, for instance, the NVProf profiler, which will help you with identifying both the CPU hotspots in your code, but also understanding how the GPU performance works. It includes the GPU wizard, which has several accelerated libraries for linear algebra and things like that. It will help you understand, here is a place in my code where I can take advantage of a library. Also, some code examples and documentation. And the one that I would really like to point out to you is the best practices guide. If you read through that, hopefully it will really help you get going. And I encourage you that if you read this and can have some feedback, to send that to us, and so we can further improvement. So this is not required for you for this course. If you don't have access to NVIDIA GPU, we will be providing free access to NVIDIA GPUs. But if you do and you'd like to try this on your real application, I encourage you to download the toolkit. One thing to note, it is Linux only, but I'll talk a little more about that in about 3 slides. So to get the toolkit, go to this website, again, developer.nvidia.com/openacc. Hit this download link in the top right. You do need to register, so it'll provide us some information. If you are a university developer, so again, professors, students, and the like, this I've circled down here where you should check and let us know so we can provide you with the free license. What to expect is that you will get an email from us with a quick link to the quick start guide that'll tell you how to install it, and also you'll get a separate email with your compiler license. So that's the process to expect as you do this. Now I do need to note, again, this is only available on Linux. However, all of the parts are available to you on Windows and Mac. The toolkit itself is a single package, single install. If you're on Windows and Mac, you have to take a little extra step. The Portland Group compiler is available on Mac and Windows, and here's the link to where to get it. Definitely still register for the OpenACC toolkit, because the license file we send you will work on Windows and Mac, so you'll still get the 90-day trial. Since you won't be getting the libraries and tools, you'll need to download and install the CUDA toolkit, and so this is where you can get it. Lastly, that OpenACC guide is available from this link. So all of this is available to you. Unfortunately, it just takes a few extra steps if you're on Windows or Mac in order to get that. Now, for the rest of the course, we're going to be using a system called Quick Labs to get you access to GPUs. All of the homework, you can do it on your personal machine, but we encourage you to do it on Quick Labs because everything has been well tested there, and we know that it will work. And you don't need a GPU, you only need a web browser to make it work. So go to this website, nvidia.quicklab.com, and either if you've done a lab before, you can simply sign in, or you can create a new account. Throughout this course, we're going to have several labs that are made free. They are free right now and will remain free through the extent of the course. So that brings me to this week's homework. This week's homework is to go through the 2x in 4 steps Quick Lab. This is available both in C and in Fortran, so choose the language that you're most comfortable with, or do it in both if you'd like. All of this is done within your web browser, and so you don't need your own GPU to do this. You'll simply fill in the code in the web browser, hit submit, and it'll run on GPUs in the cloud. This should only take you about an hour, so you should have plenty of time over the next 2 weeks to do it. And if you run into any problems while you're doing this course, while you're taking these labs, bring your questions next Tuesday to the office hours, and we'll try to answer them there. An optional piece of homework is, of course, to go install the OpenACC toolkit if you would like. This is not required at any point during the course, but I encourage you to do so you can begin looking at this in your on your applications you care about. One more thing that I'll note about the 2x and 4 steps, this is the exact same sample code that I just showed you. So if you get lost, you get stuck at any point, come back to this video and we can walk through it and hopefully get yourself unstuck. If you do have trouble, there's several places you can find help. First off is the recordings for this course. They will be posted as quickly as possible to the course website. Additionally, if you have questions, go to Stack Overflow and tag them with OpenACC. A bunch of us will be watching there looking for questions, and hopefully some of you will be looking as well. So if you finish the course and see someone else has asked a question, jump in and answer it, and then that would be really helpful. And lastly, of course, I've already mentioned the OpenACC toolkit download. Some additional resources you might think about checking out. So the NVIDIA developer blog known as Parallel for All has several OpenACC posts that have been written, some by myself, some by some of my colleagues. I encourage you to check that out, and we do have some OpenACC blog posts in the pipeline. Also, there's a variety of talks at the GPU Technology Conference, the GTC, and the OpenACC website. So to close out, and I'll begin going through chat to take some questions here, do want to remind you that next Tuesday we'll be having our office hours for this week. Bring your questions about the lab, about any questions about this lecture, or any questions about installing the OpenACC toolkit, and we'll try to help you there. And then on October 15th, which is back on Thursday, will be the next lecture on profiling and parallelizing your code. So we'll go into a lot more detail on those steps. With that, that's the end of the lecture portion. If you have any questions, please put them into chat here, and I'll begin to go through here. So if you give me just a moment, I'll begin searching through to find some questions here. One question that was asked earlier, what is the basic difference between CUDA and OpenACC? So CUDA is a very low-level explicit approach to programming. So I'm going to take my code, I'm going to break it down to the most basic parts, and I'm going to explicitly map my parallelism to the GPU. So it's far more explicit, and for many people, if they find it, if they don't have a background in parallel programming, to be more difficult to do. OpenACC is a high-level approach where you can take your existing code, as long as it's in C, C++, or Fortran, add directives to your code, and allow the compiler to manage the parallelizing for you. So it's a much more implicit approach and is hopefully simpler to use if you're not a computer scientist, if you're more of a domain scientist with a basic programming knowledge. Another question that came up is, can the compiler reject a directive if it thinks the loop is not parallelizable? And in many cases, yes. So in this week, we've talked about the kernels directive. And the kernels directive, the compiler is doing the analysis, and if it thinks it can't be parallelized, it won't. There's another approach that I'll be talking about in 2 weeks where if I want the compiler to listen to me, and I say, yes, this is definitely parallel, I want you to parallelize it, you can be more explicit and the compiler will follow that. And that's known as the parallel directive, and we'll discuss that a little bit later. I believe this goes back to the graphs. Let me find the graph here. There was a question about how much how much does the CPU contribute to this speed up number? And what I'm showing here is if I take those loops and parallelize those loops on the CPU, I get almost a 4x performance improvement on 8 cores. If I run those same loops only on the GPU, I get an additional 5x on top of that. So in this, in the green bar here, the only work that's being done on the CPU is going around that while loop, that while iteration loop. All of the actual work is done on the GPU. Another question here is, will OpenACC replace CUDA completely in the near future? And I would say no. They are definitely complementary approaches. So OpenACC is high level. It's designed to be portable. It's designed to be approachable. CUDA is a much lower level approach for when you need the explicit control and really want to take control of the parallelization. So we definitely plan to continue the development of both OpenACC and CUDA well into the future. And they are fully interoperable. So my personal approach is to start with OpenACC, and then if I hit something that is just too performance critical to do anything else, then I'll use CUDA to get that last little bit. Another question that came up here is OpenACC an NVIDIA standard or is it an industry standard? And it is an industry standard. NVIDIA is a member, as is Cray, as is AMD, PathScale, Oak Ridge National Lab, University of Houston, and there's a variety more. So it is an industry standard, and it is developed by a group of companies all working together. This question, where do parallelism libraries like Thrust and Bolt fit in? Thrust is another approach to parallel programming. Thrust is a C++ template library for parallel programming, and it's really a complementary approach. In fact, I do have some examples where you can use Thrust and OpenACC together. And so it's simply another approach to programming, and you can use it together. Another question here is when I've offloaded this code to the GPU, so let me pull up some code here to show. When I've offloaded these loops to the GPU, does it run asynchronously with the CPU? So as it is written here, what will happen is the CPU will synchronize at the closing curly brace of the kernel's directive. I can, in fact, make my work asynchronous, and in doing so, if I had something else that I needed to do on the CPU that was completely independent, I could launch my work to the GPU, let the CPU do something else, and then synchronize them at a later time. That's discussed specifically in Lecture 3, and you can look up the async clause of OpenACC for that. How does the PGI C++ compiler compare with others like GCC and Cray? They're all great compilers. At any given time, for any given code, you may find one compiler is faster on your code than another. And so it's really varies from code to code what will be the best approach for you. If you have access to the Cray compiler, that is a great compiler. If you have access to the PGI compiler, it's also a great compiler. And GCC, of course, is a very widely used compiler. GCC does now have support for OpenACC, but it's very limited at this point, and development is moving very rapidly, but still very limited. And so I would expect you would see better performance out of PGI and Cray than GCC, but which you would see between PGI and Cray, which performance you would see better, it will vary from code to code. I encourage you, if you have cases where you've tried both and one is doing much better than the other, to let us know so we can try to look at that. Going back to the graphs here, there's a question of how this code was parallelized on the CPU, and the CPU threads were managed using OpenMP. What else do we have here? Can I use OpenACC in Visual Studio Community 2015? So Visual Studio does not provide support for OpenACC. You can, however, use the PGI compiler on Windows to get that speed up. There is a question up here about the differences between OpenACC and OpenMP, which is a great question that I'm asked all the time. And so I do want to point out that I am a member of both technical committees, and so I'm going to try to answer this as fairly as possible. OpenMP has a much longer standing. It has been around for almost 20 years and was originally designed for shared memory parallelism. So it takes a similar approach where I take a loop, I put a pragma on that loop, and it gets what they call work shared across OpenMP threads. OpenMP was designed to be very explicit, to be very simple to implement. And if you read the specification, it actually does say that OpenMP does not require any sort of parallel analysis or automatic parallelization by the compiler. OpenACC was started by OpenMP members, so all of the original members of OpenACC were members of OpenMP, and most of the current members of OpenACC are also members of OpenMP. OpenACC was designed for a limited subset of what OpenMP provides. It was designed for very scalable parallelism for devices like GPUs and Xeon Phis and the like, where you need more parallelism. So it took a slightly different approach where we really focus on the things that scale well and explicitly leave out things like synchronization, which are difficult to do in a scalable manner. The two specifications are being developed right alongside each other, and there's several of us who are contributing to both. OpenACC was designed to be performance parallel, and OpenMP was designed to be functionally parallel. And so you can program with either and get good results. OpenMP will be very explicit. OpenACC, you'll be relying more on the compiler. So there's trade-offs to be made in both of them. OpenACC, in terms of GPUs, is much more mature for GPUs, and so that's why we teach OpenACC. There are more mature OpenACC compilers for GPUs, whereas OpenMP compilers for GPUs are just now starting to emerge. Let's see if we can come down here. Looks like time for probably 2 more questions. There was a question about what exactly is meant by the tile clause, and I did kind of go through that quickly because it will be covered in a later lecture. But the tile clause is going to take these 2 loops, the J and the I loop. It's actually going to implicitly add 2 more loops around them. And so when I go through this whole calculation, I'm going to work on 32 iterations of the J loop and 4 iterations of the I loop in a very small tile. And when I complete that tile, I'm going to move to the next tile of 32 iterations of the J loop and 4 iterations of the I loop. And so what that does is it exploits the fact that all of my calculations are done in a very localized way. And so it allows the compiler to work on these localized pieces of data which fit well into the small GPU caches. And so that's what's going on here. Again, come back in a few weeks for the lecture 3, and we'll go into more detail about these optimization flags. There's a question here, can OpenACC be used with MPI? Absolutely. MPI is used to communicate between the nodes, and OpenACC is generally used to exploit parallelism on the node. Again, in lecture 4, you will be doing some work where we'll actually show you a code where we've used OpenACC with MPI. I think the follow-up question to this is probably, does it work with GPU direct RDMA, which is a direct GPU to GPU MPI, and it does work with that as well. So absolutely. There's a question here, can I use OpenACC inside of PyCUDA kernels? And unfortunately not. OpenACC is strictly C, C++, and Fortran. Now you could use OpenACC inside a C or C++ function that you call from Python. That could be done, but OpenACC does not work with Python. And the same would be true with things like MATLAB and things like that. If I can find one more question to answer here, and then the rest of these questions we'll have to defer to the office hours next week. One question that came back up with the tile directive, does tile put data into the GPU shared memory? And that is up to the compiler. There is a directive where it's known as the cache directive, where I can tell the compiler I would like to put something in the into shared memory on the GPU. I would cache that into the shared memory on the GPU. I've actually, when I've tried that in this specific code, have not seen a additional speed up, and it could be that the compiler behind the scenes is using shared memory here. I have not explicitly told it. So with that, Julia, if you'd like to close things out with any announcements you have, I thank everybody for coming, and I hope, let me put the schedule back here, I hope you'll come back for office hours next week to answer the rest of these questions, and again in 2 weeks on October 15th for the next lecture on profiling and parallelizing.
Okay, thanks a lot, Jeff. That was amazing. We have really a flow of questions. We're answering them as we go. We're also collecting all of them together, and we will send you back the answers, whatever we didn't have time to answer today. And there are really a lot, so we didn't answer all of them. And again, a reminder, there will be an office hour on Tuesday, October 6th. So we'll go over the questions there as well. And yes, please use the forums. The Stack Overflow is a really good resource to go there. We will be closely monitoring that as well. Okay, and again, if you have any additional feedback, there will be a survey right after this webinar window close, so please take a couple minutes to answer those. We really appreciate your help with improving the course and adding probably more content going forward. Again, if there are any questions, use the forum, email us, and we'll be sending all of the recordings and slides together with the answered questions to you after this call. Again, thanks a lot. Thanks for joining, and see you on Tuesday.